do is I'm going to look at about 4 or 5 problems, but more importantly is how to calculate the first moment of area, where a lot of students have a lot of problem. Okay, so example number 2. Okay, so I'm going to take this image over here. Oh, myself, I start example number 2 on a new page. Okay, so example number 2. So let's read on the terms over here. Determine the average shear stress developed in the nail within region AB of the beam. Okay, the nails are located on each side of the beam and are separated 100 millimeters apart. Each nail has a diameter of 4 millimeters. Take P is equal to 2 kilonewton. Okay, so let's look at. So I'm not going to calculate the IZZ. Okay, or before we start, we are going to calculate the average stress developed on the nail. Okay, so if this is our transformation, this is our X, and this is our Y, and this is our rotation in our Z. And this P over here is going to be 2 times 10 to the power 3. Okay. And then we have to determine what is our what we have to determine the shear stress acting on the nail. Okay. So before we go on, we are given, not given, you have to find, but I'm not going to waste time on that, is that our Y bar, okay, is equal to 0.14 meters. So if it's 0.14 meters, I'm going to say that is from bottom. And we are given that IZZ is equal to, wait, let me see the IZZ. The IZZ is equal to 53.333 times 10 to the power minus 6 meter 4. Okay. So let's handle the problem first. That we are given the spacing. So let's formula what's going on. Okay. So we know Q is equal to force resistance of fastener, and then divide by spacing, right? And we know the spacing is, so S spacing is given to us as 0.1 meters, right? It's given to us by 0.1 meters. Okay. And we know, so to find the stress acting or on the nail, stress of the nail, is equal to force divided by area. And the force over here, or force resistance of fastener. So some of you will say, Eugene, you know what you are saying, that the shear stress that I've drawn down here, right? Hey, hold on. The shear stress that I drawn down here, right? This shear stress is acting here. But how can that shear stress fail the material or fail the nail? Because of the equilibrium shear stress. We know that there's another shear stress acting this direction, right? This is caused by this. So this shear over here is the one that will shear the fastener. Now you see it better now, right? How come the resistance force can be used to also calculate the shear stress? That's how it works, okay? So now, right? So now we have to calculate. So we now have to calculate the force resistance of the fastener. So we have to determine Q, right? Q. So Q is equal to Vy over Izz QZ. So Vy. So let's look at Vy. Okay, so some of you I know will have issues with Vy. So we are going to look at the highest value of the shear force. Okay. So if we were to draw the free body diagram, this will be your AY. Okay, there's your AY. And we know in a cantilever beam, this section over here, okay, this section over here is our failure point. Okay. At the cross section, this is things get really interesting. Okay. So now this is now my X. This is now our Y. And this over here is now our Z. A very interesting thing now is, so we know that the failure point will be at point A, right? But specifically where it will fail, right? Specifically where it will fail at the where? At the joints. Can you see that? It will fail at the joints. Okay. So to find AY, right? So if I were to draw, so we have to determine Vy, right? So we know that if we draw the free body diagram, what we have over here is 2 times 10 to the power 3 Newton. And then we have a load down here, which is 2 times 10 to the power 3 multiplied by 1.5. So this is 2, 1.5 is equal to 3 times 10 to the power 3 Newton. So we know that we have a what? AY, right? And then we have a counter moment, okay, because it's cantilever moment about the z-axis at point A. Okay? But we don't need to determine that. We want to determine what is our shear force. Okay, so we apply static analysis. Dimension of forces in the y direction is equal to 0. So we have AY minus by 3 times 10 to the power 3 minus by 2 times 10 to the power 3 is equal to 0. So AY is equal to 5 times 10 to the power 3 Newton. So we realize that AY, this is also equal to our Vmax. Okay, our maximum Vy. Okay, so Vy that we're going to use in our analysis is 5 times 10 to the power 3 Newton. Okay. So we now know that Q, okay, is equal to Vy. Next, we need to calculate our Qz. Okay. Qz is equal, okay, so determine our Qz. Okay. So we know that the structure, we know that the structure, right? So this is the flange member, and this is the come on, Eugene, and these are the webs. Okay. Right, we know this. And then we have two fastener, one over here and one over here, right? So the shear stress or the shear flow need to distribute this entire section, right? So remember the rule, the member will distribute the load, the fastener will transmit the load. So that is the first moment of area you have to take. Okay. Later on, I'm going to do more examples, will get more confusing. Okay. So this is quite straightforward to see. And from here, so we know that I'm going to point to the image. So I would not keep on flipping the page. You get headache, I get confused. So by looking at the geometry, right? So we know that the QZ the width is 0.2 meters. The depth is 40 millimeters. The Y bar, so we know that from the top is what? From the top, the Y bar from the top is 0.14, right? So it's equal to 0.06 minus by 0.04 divided by 2. Okay. So this will be equal to 0.06 minus 0.04 divided by 2 times by 0.04 times by 0.2 is equal to 320 times 10 to the power minus 6 meter cube. Let me do it again. 0.06 minus 0.04 divided by 2 times by 0.04 times by 0.2, 320. Okay. So from here, we know that our Q, right? We know that our Q is equal to V 5 times 10 to the power 3. Q 320 times 10 to the power minus 6. Then divide by our I 53.333 times 10 to the power minus 6, right? And then this will be equal to the force resistance is equal to what? Is equal to 2 kilonewton. No, not 2. The force resistance is equal to we don't know the force resistance. Okay. So it's equal to force resistance of fastener divided by the distance. Okay, so the distance we know is 0.1. And then we have to multiply by 2. Why we have to multiply by 2? Because if you look at look at QZ where shade in red, over here is fastener number 1, Over here is fastener number 2. Okay, so that's why you have to multiply by. So I'm just going, for simplicity's sake, I'm just going to call force resistance.